Atoms have three distinct electrostatic interactions with each other. The electrons repel. Similarly, the nuclei repel each other. Finally, the electrons on each atom are attracted to the nucleus of the other atom. When this attractive force is greater than the combined repulsive forces, a chemical bond forms. The energy of two atoms varies with distance, according to the interplay of the attractive and repulsive forces between them.
It's amazing that bonds form at all when you think about it, because wow, why would the atoms want to come together? It's kind of cool. When it comes to covalent bonds, which is the sharing of electrons, you have to remember that there's both attractive and repulsive forces when those two atoms come together, because you don't have the positive one, negative one ionic charge at this point. Everything's being shared. So on the left-hand side there, the little black dots, those are the nuclei of the atoms, and the kind of gray, I don't know what color that is exactly, but anyway, that's the electron cloud around the nucleus. Now, opposites attract. So the positive nucleus on one is attracted to the electron cloud on the other atom, and vice versa. The positive nucleus on the second atom is attracted to the electron cloud on the first atom. But there's also repulsive forces, because electrons don't want to be next to each other, and the nuclei don't want to be next to each other. So it's a combination of these forces that has to be overcome if you're going to make a covalent bond. And what this means is that sometimes covalent bonds just won't form, all right? You're going to have more repulsive forces than attractive forces, and it's just not going to happen. Now, on the right-hand side, that little video right there, it showed that there is going to be some optimum distance where you have the best overlap, the best bond, best covalent bond. And if you're too close, the repulsion gets too high. It's not going to happen. But on the other hand, you get too far away, then the attractive forces can't kick in, and you won't make a bond at all. So there's always going to be some optimum bond length that's going to happen, and every two sets of atoms will have their own optimum bond length. Now, in addition, when it comes to covalent bonds, sometimes you have perfect sharing between two atoms. So, for example, if you have two nitrogen atoms, they're going to share electrons to the same amount. Nitrogen will share its electrons with the second nitrogen to the same extent that the second nitrogen will share with the first nitrogen. And they call those pure covalent bonds, or just covalent bonds. But what happens most of the time is that you'll have two opposite atoms, like maybe a nitrogen and an oxygen, or a nitrogen and a carbon, something like that. And each of those will have its own sharing abilities. You're going to have unequal sharing of the electrons, and they call that polar covalent. So we'll talk a lot about polar things. Polar things are when you have atoms in a molecule that don't share electrons to the same extent. Hydrogen monochloride, HCl, is an example of a polar covalent bond. Chloride, we're going to see, it pulls electrons a lot more than the hydrogen does. So notice this weird nomenclature. This is a delta. It's a lowercase Greek letter, and you can see there's a delta negative by the Cl and a delta plus by the hydrogen. So this delta symbol says that the chloride is pulling more electrons its way. It's more like a negative bond, and the H doesn't pull as well, so it has less electrons around it. It's going to be the more positive side of the dipole. So HCl is a polar molecule. It has two dipoles. It has a negative dipole by the chloride, and it has a positive dipole by the hydrogen. And most bonds are this way. They have slightly positive and slightly negative centers, all right? Unless you have something like N2 or O2, or if you have two atoms that are the same in a bond, most of the time you'll end up with these polar covalent bonds where you have dipoles. Now, if you have a dipole moment, that's actually a measurable amount of dipole, and this is a pretty cool kind of thing. A polar molecule, if you have it, will actually align itself in an electric field. So notice in the bottom part right there, there's a positive and a negative. Well, remembering the opposites attract, those triangles there represent molecules, and the white triangle, those are going to be the delta negative, the negative side. sides. They're attracted to the positive sides. On the other hand, the blue triangles, those are the positive dipoles. They're going to be attracted to that negative part on the right-hand side. So polar molecules, you can sometimes separate them from nonpolar molecules by putting them in an electric field. Now, on the right-hand side, it shows what nonpolar molecules do. They could care less about your positive, negative centers because they don't have anything to be attracted to. They just kind of sit there and float and stuff like that. So this is kind of a cool way, and they do this sometimes with DNA and stuff. If you see this little symbol, this is mu. It's a Greek letter. This is actually a measurable amount of dipole. It's usually measured in something called a debye. You don't need to worry about that, but people can measure how polar molecules are, and it's kind of cool. If you're curious how polar an atom can be, it's definitely something that can be figured out, and it's figured out through something called electronegativity. Electronegativity gets the symbol chi, which looks like an X. It's really a Greek letter, but that's okay. If you write an X, it's not a big deal. But anyway, electronegativity is a measure of an ability for an atom to attract electrons to itself. And if you look here, this is the periodic table, and generally speaking, electronegativities get bigger as you get up and to the right on the periodic table. Now, couple of things. Fluoride is the most electronegative of all. Fluoride has a value of electronegativity of 4.0, which is very high. It's the highest one of all of them. And you can see that more or less as you get farther from fluorine, the values begin to go down. So generally speaking, electronegativity gets bigger as you go up and to the right, or it gets smaller as you go left and down. Either way you want to think about it. Notice the noble gases aren't there. Noble gases don't usually react to make compounds, and they're usually exempt from electronegativities. But in advanced circles, sometimes they will assign electronegativities to the noble gases, but that's something we probably won't see. So electronegativity is what we're going to use to talk about most polar and less polar. So as an example, let's say you had a carbon and a fluorine bond, and you were curious which side would have that delta negative. It would be more negative, or delta positive, more positive. Well, the bigger electronegativity would have the negative side, so that's going to be the fluorine. And the delta positive, the one that isn't pulling electrons as much, that would be the carbon, because it has a smaller electronegativity value. And you could compare atoms for everything on there. And some of them have the same electronegativity values like nitrogen and chlorine, but overall the differences are what allow then these polar bonds to be figured out. For Chemistry 221 through Chem 223, if the atoms are different, we're going to assume that they have different electronegativities and they will be polar, even though really we should look at the values to compare. When it comes to electronegativities, fluorine has the maximum value of electronegativity. And again, going farther from fluorine, the values tend to get smaller. And generally, it goes left and down to figure out what kind it is. Now, in some books, they will use differences in electronegativity to find out if you have a pure covalent, polar covalent, and ionic bonds. We're not going to follow this very carefully, but I do want you to know about it if you hear it. And in our book, it says that a pure covalent is if you have electronegativity difference of less than 0.4, polar covalent 0.4 to 1.8, and ionic is greater than 1.8. There's controversy about this. We're not going to follow it real careful. What's important in our class is that you'll only have a pure covalent bond if you have identical atoms, so two N's coming together, two F's, two O's, those kind of things. If there's differences in the atoms, like an N and an O, or an N and an F, then you can assume it's going to be polar. And if it has a metal in it and a nonmetal, we'll consider that it's going to be an ionic bond. So if you hear these kind of things, this is where they're coming from. It's not a big deal, but it does sometimes help you to understand what people are saying. So here's the kind of question you might see. It says, which of the following groups of elements is arranged correctly in terms of increasing electronegativity? And you kind of need a periodic table for this. Periodic tables will help you see which ones, where the patterns of electronegativity go. And remember that fluorine is the most electronegative, and as you go left and down, you get farther and farther away from fluorine, and the values of electronegativity get down. So if you want to increasing electronegativity, you definitely want to make sure that your fluorine is at the end, because that's the biggest one, all right? And then you want to kind of go left and down from there in order to figure out the patterns of electronegativity. So aluminum is definitely most left and down of that list of 4 elements, all right? So aluminum will be the least electronegative. And then if you go up, you'll get to boron. So right above aluminum on the periodic table is boron, so that would be next. And if you go right, you'll get to oxygen, which is second highest in electronegativity, by the way. And then finally, you'll get to fluorine, which is the king of the electronegativities. So the answer C here would be the right one. That would be the order of increasing electronegativity. And notice how we went up and to the right in order to figure that out on the periodic table. You don't have to have the values of electronegativities in front of you. You can just use the periodic table and it works pretty well. So here are 2 bonds, an OH bond and an OF bond. And the question is here, which bond is more polar? Now you can also see this as which one has a more dipolar interaction, and dipolar would just mean the biggest difference in electronegativity. So for a question like this, I would refer to an electronegativity value of table or something like that. I would look up oxygen, which is in both, and then compare oxygen to hydrogen and oxygen to fluorine. So if you do that, you see the oxygen has a value of 3.5, and you can look back on that table if you'd like. Hydrogen is 2.1 and fluorine is 4. So what we'll do here to answer this question is we're going to find the difference in electronegativity, delta chi. So 3.5 minus 2.1, that's the difference. That would be 1.4. And the other two, just think of an absolute value. 3.5 minus 4, of course, is minus 0.5, but we just care about absolute value, so let's make it positive 0.5. If you want to call it negative, it's no big deal. Anyway, these numbers are helpful to chemists because an OH bond has a bigger delta chi, a difference of electronegativity, than OF. So that means that OH is more polar. And in this context, what that means is hydrogen's going to be definitely more of a positive side, and oxygen will be more of a negative side. You'll see a positive negative on OH a lot more than you would have on OF, because OF doesn't have as big of a difference of electronegativity. But the other interesting thing about this comparison is oxygen has a bigger electronegativity than hydrogen. So that means that oxygen's going to be negative when it's compared with hydrogen. But with fluorine, fluorine has a higher electronegativity. It's the biggest of all. And notice that the oxygen is actually the positive part when it comes to the OF. So the polarity is, if you will, reversed. Oxygen is negative with hydrogen, but it becomes positive with fluorine. And that shows how versatile these elements can be. And it also shows the value of electronegativity values. So here's a question you might see. Here are 5 different bond types, and it says, which of the following will be expected to have the greatest bond polarity? Now, in this problem, we don't probably have a table of electronegativities next to us, but if you did, you could absolutely use a table, and you could compare. You'd look for the biggest delta chi, like we did on the last example. So if you don't have a table of electronegativities, what you want to do is you want to pick the 2 elements which are furthest from each other on the periodic table. So looking at that list then right there, first of all, the very last one, F and F, even though fluorine's most electronegative, that's a fluorine with another fluorine. So delta chi, the difference of electronegativities, would be 0 for that. So that's actually a non-polar bond. There wouldn't be any difference there. And if you look at all those different ones, notice how answer B has a potassium. Now, potassium is on the far left of the periodic table, much farther than anything on that list, to the left anyway. And fluorine is definitely far to the right. So the biggest difference between the elements would certainly be K and F. So this would be the way to answer questions like this without it. The atoms that are farthest apart will have the greatest bond polarity. KF isn't just polar, it would be truly ionic, because you have a metal and a non-metal. So that would have a true positive and a negative center. No sharing of electrons here. But even from that, we can find that potassium would be the positive part, smaller electronegativity, than fluorine, which has a bigger electronegativity.